So now, hi class, we are on chapter 5.2 and we're going to start looking at ions. So many chemical compounds are composed of ions. Remember, ions are atoms or a group of atoms that have an overall charge. So they're not neutral. They either have more protons than electrons or more electrons than protons. So we're going to look at different types of ions and learn how to name them. So when we first got started a long time ago, I had brought up the word cations, even though your book had not brought that up yet. So I was trying to bring in something beforehand, get you used to it. So cations are positively charged ions. So not just ions are general, cations are specifically positively charged ions, meaning they have more protons than they do electrons. Atoms form cations by losing electrons. Main group metals form cations in order to fulfill the octet rule. So for sodium will lose that one electron. It's in group 1. And once it does that, it becomes an ion. But also by doing that, it takes on the configuration of neon, and it fulfills that 8 octet rule by kicking out or giving away that last electron. So again, so then it ends up with sodium having the electron configuration of neon, and that gives it gives up that one electron from the 3s sublevel, and then that means it's electronically identical to neon, which is a very stable arrangement that fulfills the octet rule. So as a result, sodium does lose that one electron to form a sodium ion or sodium cation, which means it has more protons than electrons, but it actually becomes more stable. So Lewis structure shows cation formation. So looking at a Lewis dot structure, sodium begins with 1 electron in its valence group. We're looking at group 1, and all of those lose 1 electron. When sodium loses that 1, it attains the same electron configuration as neon, which we already discussed. Because it loses 1 electron, it now has a +1 charge. Why does it have that? Because the electrons and the protons are no longer balanced, and it means it has more protons than it does electrons. So when you see something that's positive, that means that the protons outnumber the electrons. When you see an element that is negative, it means that it has more electrons than it does protons. Magnesium is an alkaline earth metal. It's a group 2, so it will lose 2 electrons. So with it will lose those 2 to take the same configuration as neon. So by losing those, it results in a +2 charge, but it will take on the electron configuration as neon. So this is where the 2 charge comes from, because it has to lose those 2 in order to take on that neon configuration. Okay, so I brought in, these slides are from previous I brought in, and I told you guys to ignore this top portion here. Well, now this and this should make more sense. Where you can see for sodium, it loses the 1, it becomes an ion. It becomes smaller because it loses that outer shell when the electron goes away. But you can see the electron configuration as an ion and as a neutral. So hopefully this comes back to you. Magnesium's the same. Magnesium Lewis symbol is this as neutral, but once it loses them, it becomes an ion. And you can see the electron configuration for that too. And it becomes smaller because it loses that outer electron shell. Okay, so transition metals. The transition metals are D block. They are in the middle here. And they lose electrons to form positively charged ions. However, transition metals do not follow a simple pattern like main group. That's why we talk about them after we learn those, because they lose all sorts of different charges. They can lose 1, 2, 3, 4, some lose 6 electrons, some I think even lose more than that. Other books call these oxidation states. For some reason your book hasn't talked about that yet, and I know it will. So we call these different oxidation states. It's losing electrons. Transition metals typically form ions having a charge between 1 and 4, but some metals can form multiple. So meaning they can, for instance, here you see iron can lose 2 electrons or can lose 3. Chromium can lose 2 or 3. Cobalt can lose 2 or 3. Copper can lose 1 or 2. And then there's some that only lose, like zinc only loses 2. It doesn't have different oxidation states. And silver only loses 1. So some metals in the lower part of the p block also behave this way. They here are some ions in the d and p block. So you can see that even some in the p block have, this is lead, actually loses different electrons. So metal naming cations. So in general, metal cations are given the same name as neutral metals. So we have to learn how to name them now. Examples, the cation produced from sodium metal is called the sodium ion. The cation produced from magnesium is called magnesium ion. Some transition metals can have more than one charge. For instance, iron has either a 2 plus, loses 2 electrons, or it loses 3. So it has a 2 plus charge or a 3 plus charge. There was an older way of naming these. And so for iron that has a 2 plus, we would call that ferrous, a ferrous ion. And the iron that had a 3 plus would call ferric. And the ending of OUS or IC, would tell you which one you're dealing with. Now, in modern ways, we don't do that. We write it out with Roman numerals. So iron, no space in between, and it would be 2 matching this, or it would be 3 matching this. And so you still might run into this and this, but normally we only go by the modern name now. So for instance, again, you write the name out, parentheses with no space, and then the Roman numeral number of that oxidation state, that charged state, would be in the parentheses. Why? Because this charged state goes with this iron. It doesn't go in the middle with a space. If you write it with a space, it's wrong. It has to be directly next to the iron to show that the oxidation state, that charged state, goes with that element. Same as with copper. Copper, the old way was cuprous for the lower oxidation state and cupric for the higher charged state. So copper, no parentheses, would be 1 because the plus sign is a 1, and then we have a 2. So this is how we normally write them now. This is the older way. This is what you need to learn. So I have pulled some slides from another of my courses so you can see. Transition metals of zinc, cadmium, and silver form 2 or more positive ions. That means that silver loses 1 electron, cadmium and zinc lose 2. They, however, do not have different oxidation states. That's all they're going to lose. They're not going to lose any more electrons. So the nice thing about those is that they don't use Roman numerals because they only have 1 oxidation state. So it would just be zinc, no parentheses, no nothing, cadmium, no parentheses, no nothing, and silver. That's it. But when we look at the other ones, we have to account for those oxidation states, and that's where you can see I've given you some examples from some of my slides that are not from this book. And this is also not from this book, but I've given you some charges so you can see in the middle that there are. See, silver doesn't have another one, zinc doesn't have another one, and cadmium doesn't have another one. So these are slides from another book, another school. And this is how we're going to break it down. So you have the name of the cation. We haven't discussed this part yet. The name of the cation, and then in parentheses, the Roman numeral with no space in between. We haven't even discussed the anion yet. But this gives you a structure, a formation, so you understand how to write this out. Again, these are some more of my slides. If you don't know Roman numerals, I've enclosed this here from other slides of mine, so you can understand what these are. And then here are some examples of just more of them, so you can get used to them. And remember, see, SN is tin. So not all of them match up. Hg is mercury. They don't all match up. Manganese is Mn. Do not get that confused with magnesium. All right. So this is saying exactly what I talked about. These do not have different oxidation states. Silver, zinc, and aluminum. Oh, this one's saying aluminum. I guess it doesn't want to. Okay, so your book's not going to count cadmium. That's fine. These 3 have these charges, so you wouldn't need to use Roman numerals with them. Same as with these metals, because they only lose 2 or they only lose 1. We don't use Roman numerals. We use them for all the rest. Again, here is an example of, you can see the older way of naming and then the newer way of naming these. Okay, so let's practice naming these. So for name the following cations. So for Ag, that's silver. For lead, 2, this is a 2 charge. So lead, no space in between with a 2. And then we have lead 4. So you would look up the Roman numeral. I gave that to you, so if you need it, reference that. And you would write it with no space in between. Now we're going to look at anions. Anions are negatively charged ions. And they are specifically negatively charged. So instead of saying ions as general, you say anions. They have a negative charge, which I already said. These are nonmetals located on the right-hand side of the periodic table. And anions, let's go to the next slide. Anions fulfill the octet rule. So where metals or cations, they give away electrons, anions take the electrons. Those electrons have to go somewhere. So the valence shell nonmetals are completely full, so by taking these electrons. To fulfill the octet rule, these atoms gain electrons, giving them a negative charge because now they have more electrons than they do have protons. So for instance, fluorine is a halogen, so it has space for one electron to make it fill an octet. So gaining one electron, it achieves an electron configuration of the noble gas that's here, which is neon. It fills that up, but it has a charge. Because of that one empty space, it gains that electron and becomes a full octet. So this is more stable as an ion than it is as a neutral, because it takes on the configuration of neon. So it has the same configuration. This configuration fulfills the stability, fulfills the octet rule, and provides stability to that ion. As a result, fluorine tends to aggressively grab an electron, forming a very stable ion with a charge of +1. It does. It's very, it has a behavior to take an electron very easily from something because it makes it more stable. The other halogens also form -1 charges to fulfill the octet. Oxygen, sulfur, and the other atoms below on the periodic table that are made up of group 6A of the periodic table. This group is called the chalcogenes, which I didn't even put on here because this is a new word. When I was a student, this name didn't even exist. Your book hasn't talked about it till now, so I didn't put it up. It's interesting because it wasn't in your reading from what I could tell, and now in my slides it brings it up. But anyways, it's group 6A. And chalcogenes, CHALCOGENS. I didn't know they wanted to use it. That's all I'm going to say about it. So each of these elements are 2 electrons short of a noble gas configuration. So oxygen it needs 2 electrons in order to get to so 1, 2. That's where it needs 2 electrons in the outer valence level. So it gains 2 electrons with the resulting charge of 2-. These atoms below also form with a 2-. So sulfur will also take on a 2-. All right, and groups 5A need 3 electrons. So they have 5 electrons, they take on 3, and that should help you look at 1, 2, 3. It needs 3 to get to an octet. Oxygen needs 2, 1, 2, and fluorine needs 1. So count how many away from the noble gases, and that will also help you. So it has 5, and the negative charges means it has more electrons than protons. So 5A, so neon and phosphorus, which is right below it, has a 3 negative charge. These atoms gain 3 electrons to fill their valence level, and they form ions with a charge of 3-. Okay, now we're going to start naming anions. So when an atom gains electrons, we name the resulting anion by changing the end of the atom to the name "ide." So for instance, chlorine now is chloride. Why? Because it's an ion now. It's gained electrons. That gives you an indication that you're not dealing with something that's neutral anymore. You're dealing with an ion. And any type of chemical reactions, that is what happens. We deal with ions. We don't tend to deal with just neutral. Chlorine atoms form chloride ions. Oxygen atoms form oxide ions. You see the Y is gone. It just pretty much cuts this off here and ends "ide." Sulfur atoms form sulfide, and nitrogen ions form nitride. So where the O ends, we drop this here and we end the "ide." So base name of an anion, nonmetal plus "ide." I got this from another one of my slides. So if we go back to the pattern, this is the whole complete thing. So here is the base name of the nonmetal plus "ide." All right, so polyatomic ions are groups of atoms that have an overall charge. So there's only one positive, and it's ammonium, which is right here in this orange, yellow kind of color, and everything else below is negative. Some have more than, you see this has a 3 negative charge, some have a 2 negative charge, and then others have a 1 charge. These you definitely have to know. I know we're online, But trust me when I tell you that memorizing these will save your life. You are never getting away from these either. If you're in 24A, you will be in lab in person. You won't have access to be able to search things up and rely on them. You'll have to, you will come in with certain expectations of knowing them. So it is in your best interest to start memorizing these now. The formulas and names for the most commonly polyatomic ions are presented in this table. You will and should know these. Notice this table contains only one common polyatomic cation, which is ammonia. I highlighted that. And the rest are anions. Okay, so polyatomic ions, group of atoms with a charge, oxyanions. Simple, they contain oxygen. That's it. Usually named as an element plus an 8. So what does this mean? Most of the common polyatomic ions contain oxygen. These are called oxyanions. We name oxyanions by adding the suffix and then an 8 to the root of the element. So the oxyanion from carbon now has an oxygen with it. So, and here on this bottom one, we have phosphorus, which now has an oxygen added. So with the element group, which is carbon, and we add an 8. So this is carbonate. This is phosphorus. It's phosphate. So now we're going to start getting into the endings and how all of this is significant to what element you're using or what group of atoms you're using. So carbonate, carbon plus oxygen, carbonate. Phosphorus plus oxygen is phosphate. All right, so we're now looking at more. All right, so some elements form more than one oxyanion. What does that mean? Some compounds have more oxygen than others. Perfect example here is nitrate and nitrite. So nitrite, and the 8 ending means it has more oxygens, and the ite ending means it has less. So those are good indications. If you're dealing with an ite ending, that means that it's got less oxygens than whatever the other one it has. So we use the suffix 8 to indicate the ion with more oxygens, atoms present, and the suffix ite to indicate the ion with fewer oxygen atoms present. So nitrate has 3 oxygens, and nitrite has 2 oxygens. However, they still both have 1 nitrogen, and they still both have a -1 charge. Okay, so here are some more. Chlorine actually has 4 oxyanions. So it has 4 oxyanions. That means it has 4 different groups of oxygens when all of them have different number of oxygens. So we use the chlorate for ClO3 minus. So that's the chlorate. And we use the chlorite for the ClO2 and a negative charge. But we also have 2 more. We have one here and we have here. So we add the prefix per, which is in blue, which means more than. So this means it has more than chlorate. So we have 4 that go with this one. And then we add the prefix hypo, which means below. So it has below chlorite number. So hypochlorite has fewer oxygens than chlorite. And this pattern is used for also, I'll discuss it right now. So this one has 1 oxygen, that's hypochlorite. This has 2 oxygens, that's chlorite. 3 oxygens is chlorate. 4 oxygens is perchlorate. Now this is chlorine, but this also follows the rules for bromine and iodine, which are also halogens. They follow the same rules as this one. All right, so I pulled this from my other slides because your book didn't give this to you. So this is what it means. It follows the same rules for iodine. You can see here, hypoiodite is 1, iodite is 2, iodate is 3, and periodate is 4 there. And the same thing goes for this. So how you name it should tell you how many. This is 1, 2, 3, and 4. Okay, so these are ions you definitely should know. You should get familiar with these and know these and the oxygen states. They will save you a lot of time and headache if you know these. All right, so let's name the following ions. So remember how to name cations? You probably don't, but let's go through it. They're the same. Cations don't change. That's the nice thing about them. We don't change. The only thing that you have to account for is if it's a transition metal, you have to use a Roman numeral. So calcium is still calcium. Zinc is still zinc because zinc only has one oxidation state. Tin has two oxidation states, so you use the correct Roman numeral. Bromide and phosphide. Which of the following is a sulfate ion? So there's the 8 ending. That means it's with an oxygen. So we have to account for a few things here. Let's take a look. Let's just go. All right. So what does that mean? We have an 8. It has 4 oxygens, but it also has a -2 charge. These are polyatomic ions you have to memorize. You're never going to just be able to wing them. Trust me when I tell you that list I gave you, learn them, memorize them. You will always get things wrong and you will never be able to wing when it comes to polyatomic ions. Which of the following is a periodate? So that one is 4. And there you go. Which transition metal does not have multiple cations? Well, I already covered this a few times. It's zinc.